Hi, welcome to the third live session of Quantity Topology 1 course. My name is Shavik and I'm working with Dr. Ramesh Kaushik of Itemetrics. We're going further. Confirm me whether I'm audible and if the screen is visible to you or not. Kindly confirm whether I'm audible and the screen is visible to you or not. Okay, thank you for the confirmation. Okay, thanks. Okay, so today we will start with one topic, namely continuity. Okay, so let me tell you clearly first that first we will finish the usual syllabus. Then we will go through some problems. Okay, I think that's better. Okay, because while discussing some things, some topics like continuity, and there are many more things like quotient topology, etc. and all. So in between, shortly we will see some problems which we in between try to solve also. Okay? First, but for today's class, we will try to start and finish with continuity. Okay. Okay. So first, tell me before starting, do you have any questions from the previous classes? You can ask any question except from the assignment whose submission date is not exceeded. If you have any questions, please ask. Yeah, there is chat. Check. So your question is Ajay, interior of Open 01, right? I mean, I don't understand that interior of yeah, okay. But what is the question actually? I forgot. Please repeat the question actually. Please repeat the question. I actually forgot. You can unmute yourself and directly talk if there is no issue in network. That's okay. Last okay. 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 Understood. Okay. Yeah. Understood. So I'm going to writing on the screen now. Let me tell you clearly that while writing there is no notification icon. See, okay. So if you have any question, you can unmute and then talk. Okay. So the question was, yeah. So we have R with cofinite topology. Now the question is that what is interior of 01? This is the question. Am I right or not? Please still.
Yes, sir.
Yeah. So look. So So anyway, interior of Open 01 is contained inside Open 01. Okay, and this is one thing. And secondly, it has to be open set. Okay, and look, R with cofinite topology. What are the open sets? Open sets. Suppose U subset of R, open if and only if U is equal to R or empty or U complement finite. Okay, this is the criteria for some set inside R to be open. Now, suppose if this interior is not empty, okay, and suppose this interior contains one element, just one element, okay, then R minus that singleton is infinite, right? So the interior point can't contain even a single element. That's why this interior is empty. The thing is that some subset U is open if and only if it is either a whole set or empty or its complement is finite. The point is that one second, if this interior contains even a single element, then no, then also its complement is infinite. So this interior cannot contain any element. So that's why the interior is empty. Do you understand?
Yes, sir. Thank you.
Okay, so okay, so let's now start with the in between also. If you have any question, please ask. Okay. So okay, so first tell me, how many of you have gone through metric spaces previous some course? I mean, how many have a separate course in metric space already other than real analysis? How many of you?
No, sir.
Okay, so you don't have any. Oh, no problem. Okay, so you have already gone through the continuity thing, the real analysis. Okay, so can anybody please unmute yourself and speak the definition of continuity, at least in the real analysis? Anybody please? Six that is for continuity, no problem. Okay, so let me take the definition continuity for the real case, then we gradually comes to formula. So in the real analysis, what is the definition? Suppose U subset of R be open and a map. We have some map F from U to R. Then let X belongs to U. Then F is said to be continuous at X if for any epsilon greater than 0, there is a delta greater than 0 such that um, mod fx minus, sorry, put it x naught, mod fx minus fx naught less than epsilon for all x belongs to um, delta neighborhood of x naught, right? This was the definition for continuing the real analysis. So usually in most of the books, we start from this definition, and then there are some equivalent definitions like the most common equivalent definition is that inverse image of open set is open, and another was inverse image of closed set is closed. This was the definition. Possibly, most of us has gone through these two equivalent statements as some theorem of the continuity. So now the thing is that in the real analysis definition, we can talk with epsilon delta, this mod thing, because in real analysis, we have some constant of distance, okay? So that's why this mod A minus B makes sense. But in topology, we have only open set or closed set, okay? So in topology, we will take the definition, I mean, so in topology, we will take either this or this to be the definition of continuity. So let me write it clearly now. Let now this definition is in the topology definition. Okay, I mean essentially same, but in topology this is the definition. that x and y are two spaces, and let f x to y be f. Okay. Then f is said to be continuous if f inverse u is open in x for all u open in y, or I mean equivalently f inverse f is closed in x for all f closed to y. So this is the definition for continuity. Okay. So yeah. So from now onwards, we will consider this to be the definition of continuity, as long as we are in the pure ratio. So now there are some equivalent definition of continuity, which I am not going to prove because some of these definitions you have seen in reanalysis course or metric space course as a property or exercise, but this can be directly proved from using these two definitions. Okay, so I am not proving those things; just I am writing the definitions. Okay, these are the equivalent definitions. So, uh, so the thing is, suppose f x to y be f, then the following are equivalent, and therefore the following are equivalent. F is continuous. Number two is for all a subset of x, f of a closure subset of f of a whole closure. Number three is for all b closed in y, f inverse b closed in y. This is the actually definition I took, but anyway, we took the definition of continuity to be the inverse image open series open open. And the fourth definition is for all x belongs to x, sorry, and each open set B containing fx there exists an open set U containing x such that f of U subset of B. Okay. So this is the definition. So these are the total four. Yeah, these are total four definitions of continuity. Okay. So whenever which one is we can directly use. So one. Okay. So now the next comes the definition of homeomorphism. Okay, so till now, anybody heard about the homeomorphism word in class or somewhere else, or have you seen this word before?
Yes, sir.
Okay, so I mean, can you please tell what is the homeomorphism? If you can recall the definition. I mean,
Sir, F is bijective
yeah,
and F inverse is open. F inverse is continuous.
inverse open and okay, no problem. So okay, so So likewise continuity, there are many definitions of homeomorphism. Okay, so first we will start with some definition and gradually we will try to prove the other definition of continuity. Okay,
F inverse is continuous.
fine, good. If inverse continuous, fine. And if inverse open, so this is same as saying that I mean, okay, it's a homeomorph. So yeah, it is if continuous. If inverse open implies if continuous. It's obvious, right?
It, it's an open map or it's a closed map, right?
Uh, no, it's a
Closed,
homeomorphism. So homeomorphism means it is bijective and continuous.
closed,
So it is open map as well as closed map.
and F inverse is open.
Yeah, if inverse open, but if inverse is continuous also, and if is also continuous. From these things, we can directly conclude that if inverse is also closed.
But
Okay.
if F is open, then F inverse is continuous.
Yeah, if inverse is open, but one can say that if in definition one can take it to be closed also.
Yeah, yeah, open or closed, either one. Yeah.
Yeah, yeah. So the definition goes as follows. Let once. Yeah, let f x to y. Yeah, such that f by f f continuous, f inverse continuous. Then if is said to be then if is said to be a homeomorphism. Okay. So this is a definition of homeomorphism. Now the point is that um, okay. So hmm, now observe some things that if continuous, this implies f inverse open, and of course f inverse closed. And this and these two things individually will also implies that f is continuous. So likewise, there are many way of proving some map to be homeomorphism, but usually the most convenient way is to showing the map to be homeomorphism is that f bijective plus open plus continuous. Usually, in most of the problem, if we can show these three things, then it is a homeomorphism. But the point is, I mean, the point of showing openness is that sometimes it's difficult to show some map is there, some I mean, inverse of some map is a closed map or continuous map. That's where directly showing that if it's an open map and continuous, hence it's a homeomorphism being bijective. Okay. So one. Okay, now there are some properties what is it, which are very useful actually, and some natural properties also. So okay, so from now onwards, whenever we need to prove some map is continuous, we need to first try to show that its inverse image is, I mean, inverse image of open set or closed set is open or closed respectively. Okay, most of the time the definition should work, but in some problem, if there is some tricky problem, then we need to do some other way around, but most of the time this definition works. Okay, so first theorem, I mean, these are not theorem, but most of the books record this as theorem. That's why I'm writing this as theorem. Okay. Yeah, so the first theorem is that let x y z displace. So f x to y be constant map, then f is continuous. So tell me how to do this. We need to show that any constant map is continuous, and the same thing you must have seen earlier. So now in topology, how to do it. Any constant map is continuous. Anybody? I mean, it is very easy, but just tell me how to do it. Anybody,
Well,
please? Yeah, please.
the inverse image would be all of x, which is open.
Sorry, I don't get it. Probably can you just repeat?
The inverse image of
Yes.
y, f of x equal to y would be all of x, which is open.
Yeah. Yeah. So I mean, yeah, you are right. So suppose all in the under this map, all x goes to y now, and if you take an open set u inside y, and if u contains y naught, then f inverse u is equal to whole of x, and if y naught does not belongs to u, then f inverse u is empty. In both cases, f inverse image of open set is open, so that's why it's a continuous. Yeah. So the second thing is that second theorem is that let A be subspace of X. Then the inclusion is continuous. That is A goes to A. So for a subspace, the natural inclusion from a subspace into the model space is continuous. So how to do this? Think about it. No, it is not difficult.
Well, the identity map is continuous, right?
Sorry.
The identity map is
Yes, yes,
continuous.
yes. Identity map is continuous, but the domain and codomain of identity map are both capital A, right? But here in case of inclusion map, the codomain is something larger. So in this case, how to do? I mean, yeah, we after some minutes we see that the codomain really doesn't matter. But till now we don't have any theorem. We need to only proceed with definition, because whatever you said, if we want to apply, so we need to actually use this theorem itself to prove that. Okay, so we need to prove this without using anything. It is easy. Think about it. Take your time and let me know.
So if you take any open set in X, right,
Yes.
its inverse image has to be open in A.
Yeah, we need to show this. So what to do? I mean, we need to calculate what is J. I mean, we need to somehow show that J inverse A is open in A, right? So what to do?
Well, it's injective, but it might not be surjective.
Yeah, I
It
mean,
might not be surjective.
no, this map is no, this map is a subjective, right? This map is a subjective, right? So first, tell me, what will be the J inverse A? What will be the J inverse A? So the J inverse A. I mean, as I said, the J inverse A has to be a subset of capital A. So which element will be inside J inverse A? Though J inverse U contains those elements of A which um, one second. Yeah, look, J. So let Y belongs to J inverse. Okay, this implies Jy belongs to U. But from the definition of the J map, Jy has to be equal to Y, and J inverse has to be subset of A by definition of J map. So this implies what? This implies Y belongs to A intersection U, and this is what precisely is J inverse A, right? Do you understand? So yeah, so the J inverse,
So,
yeah,
so could you repeat why this belongs to the intersection?
yeah, sure. So yeah, suppose Y belongs to J inverse U. Okay. Now by definition of the J map, I mean J is an inclusion from A to X. J inverse U should be a subset of capital A. Now Y belongs to J inverse U, so this implies what? This implies JY belongs to U, right? So now by definition of Jy is equal to small y. So this implies what? Small y belongs to U, and here we got also y belongs to capital A. Hence, y belongs to A intersection U. And this is what nothing but precisely J inverse U, right? Because we initially choose y from J inverse U, right? So that's why J inverse U is nothing but the A intersection.
Yes, sir. Thank you, sir.
Yeah. So yeah, so J inverse U is intersection A. Now the point is, observe U open in X. So by definition of subspace topology, this U intersection A will be open in A. So this means what? The inverse image of open set is open in the domain also. Hence J is an open map. Sorry, J is a J is continuous. Do you understand? J is continuous. Why? If you have any doubt, please ask. Okay. I hope everyone understood. Okay. So the next thing is okay, so now nextly we are going to prove the composition of continuous map is continuous. Again, it's a very, I mean, again, everybody must have seen in the real analysis metric space, but in topology this is true also. Proofs are not difficult. I mean, in real analysis, the proofs are actually difficult because in real analysis, we use the epsilon delta definition, but in topology, we are going to use the open set closed set definition. Okay, so let's see if f x to y and g.
Can I ask a question?
Yeah, sure.
This might be off topic, but since we're talking about inclusions, um, Can you talk about an embedding, or is that not
Embedding, yeah,
embedding?
embedding, yeah, embedding. Yeah, yeah. I can give the definition, but right now there is no point of introducing embedding. Okay, so I mean that's why I simply did not uh,
Yeah,
give the
okay, I
definition
just,
of embedding. I mean, after some, I mean, there is some concept of quotient topology. In quotient topology, actually, we need to use the embedding and the related theorems. So when I say at that time, we will go through the definition so that we can understand this better. Right now, there is
all
no
right.
point of giving the definition of embedding.
Okay, thank you.
Yeah. So okay. So yeah, suppose f x to y and g y to z be continuous maps. Uh, what's the statement? Yeah. Then sorry. Yeah. Then the map G compose F from X to Z is continuous. So the composition of two maps, two continuous is continuous is what we have to prove. So how to start? Anybody? Please? So of course we need to start with an open set. So tell me how to proceed really. Just only use either closed set definition or the open set definition. Try to do. I shall be back after 2 minutes. हाँ की वाला
So we can take an open set in Z,
कि खा
then because G is continuous, G inverse of that open set will be open in
तेन आना
X, uh, no, open in Y. Then we can take the same open set in Y, and because F is continuous, F inverse of this open set will be open in X. So we would end up with GOF is open in X.
Yeah, so anybody please, how should we proceed? Any idea or any guess?
So we can take an open set in Z,
Yeah.
Because G is continuous, then G
Yes.
inverse of this open set will be open in Y.
Yes. Okay.
Then we can consider this as an open set in Y, and because F is continuous, F inverse of G inverse of U will be open in X.
Yes.
Then this is same as GOF whole inverse of U open in X.
Yeah. Very good. Nice. Good. Yeah. Correct. So in this way, you can show that composition of continuous maps is continuous. So the next theorem is the following. I mean, next result actually is not. These are not theorems. These are the results. So the next result says that, yeah, suppose if x to y is continuous map and a subset of, I mean, sorry, a subspace of x, then the restriction function, so this tells that for country we have some continuous map, then if you restrict the given map to some subspace, then the restricted map will also be continuous. So how to prove it? Think about it. I'll let you know. It's quite tricky, of course, but whatever we have seen till now up to the last three theorems, we need to use this somehow, use those things somehow in order to prove this fourth one. Think about it. I mean, can we write if restricted to A in some different way? Can we write if restricted to A as a composition of two maps? Is it possible? Think about it. Because if we can write if restricted to A as composition of two continuous maps, then we are done, right? So think about it whether it's possible or not.
F of x would be f of y,
Um,
a subset of y,
yeah,
right?
yeah.
And
So
then
then,
f of y
mm,
intersect with a.
yeah.
Um, that would be the composition of maps,
Yeah,
right?
so suppose, so whatever told in means that suppose you took from open and y, then basically that f restricted to a, its inverse of u is nothing but f
Mm.
inverse u intersection a, right? Yeah. So yeah, so in this way we can also say this, or slightly fascinating way is the following, that f restricted to
So,
a is nothing but a inclusion x to y, and this is the whole composition. So each f and g are continuous and composition continuous. Both way are correct, so in both way it can be done. Yeah. So
okay.
yeah. So there's last theorem. No, there's last two theorems actually, which are actually useful. Theorem goes as follows. Suppose f of x to y be continuous. If z be such with y containing the containing image f, then the function g from x to x, x to z obtained by restricting the range of f is continuous. And similarly, if z contains y, that is, if z is bigger than y, then the function h from x to z obtained by corresponding range of f is continuous. So this is a full question. So first, so it has two parts. First, we have some map x to f of x to y, and suppose z is a subset of y, subset of y containing the image f. Then the function g x to y obtained from x by restricting the range is continuous. So this is the first part, and the second part is that suppose z is a space which is bigger than y, then of course the map h from x to z, which we are getting by expanding the range of f. So essentially these maps are nothing but x goes to fx, but here we containing this fx lies inside capital Z. So this h map and the small g map, the little g, both are continuous map. We need to show this. So how to do? Of course, just try along with the definition of the open sets. Try along with the open set definition of continuity. You can take also closed set definition, no problem. But let's try. First, tell me, do you understand the question? If yes, then try. If no, then please ask.
Well, it's just like the other one on the order of J and F is interchange. Switch around.
Sorry, can I please? I could not get it properly.
It's like the one we just did, except the injection uh, the
So
inverse the, the
yeah,
inverse
so
image of the inverse image of the injection is an open set. Right? So so if it's an open set in Z, then its inverse image.
no,
If it's
for
an
the
open
first,
set in Y, then its inverse image in
yeah,
X
for
is open.
yeah,
F
but
is
for
continuous.
the yeah, for the first part, for the first part we can't use the inclusion really, because if you want to use the inclusion you need to make some kind of composition, right? But the thing is that z uh, is
But
inside y, so that's why we
but
need to go from x to z. So and y is something bigger, and it is already given x to y, so this inclusion way will not work here actually. For the second one, the inclusion trick
Yeah,
will
but
work.
the inverse of the restriction is the inclusion, right?
I mean, yeah, that's right. But the thing is, but inverse here, yes, that's correct. But how to use that? We directly can't use that, right?
Um,
I mean,
if A is
no need to use
A is
any other thing. You can directly use the definition. Only
if
definition
U is
will work here.
if U is open
Yeah,
in what
Z Z.
Z, then the restriction intersected with U is open.
Yeah, I mean, so I mean, if U is a subset of Z, then F inverse U, that the original map is nothing but uh, well, yeah, if U is open in Z, so this U can be written as V intersection Y, while V is open in, sorry, V intersections. V is open in Y. Now try to observe that F inverse U is nothing but G inverse V. I mean, anyway, I mean, whatever it is, it's not. I mean, we can write it also G inverse of G inverse U also. So it's not a problem. So F inverse U is equal to G inverse U. But you should understand that why I'm writing directly F inverse U is equal to G inverse U, because whatever we told that the inclusion inverse is the injection. That's why we can directly write this thing F inverse U is equal to G inverse V or G inverse U, whatever, both are same thing. Okay. That's all.
So I didn't quite understand this part. Could
Yeah.
you repeat?
Yeah. Sure. Once again. So, hmm. So look, we have fx. Look, so what? In the statement, what is given, t is a subset of y and it contains image A, right? Okay. So this means we already have fx containing z containing y, and the map G is from X to Z. Okay. So what we will take? We will start with U, open in Z. Okay. So this implies what? U can be written as V intersection Y. Sorry, V intersection Y, where V is open in uh one second. Sorry, V intersection Z, where V is open in Y. Okay. So we have two sets. One is G inverse G inverse U, and another is F inverse of V. Now claim is that G inverse U is equal to F inverse V. Now the point is, the way the function is defined, it is natural that G inverse U is equal to F inverse V. Okay. So this is the reason why G is an open map. Now if inverse V is open, so that's why G inverse V is open. Now if you want to understand G inverse V is F inverse V, you try to figure out why it is. I mean, if you are getting any field, you first write down G inverse V in terms of definitions. They will automatically get F inverse V. Okay. I mean, this is it. Or yeah, or you can do one thing. U is equal to V intersection Z, Z. Okay. So you can do one thing. Uh, so you can take I mean F inverse both sides. So this is F inverse Z intersection F inverse Z. Okay. Now the point is that Fx subset of Z. So this implies what? X is inside F inverse Z. Okay. So I mean, of course. No, no, sorry. In this way, this does not miss it. In this way, it will work. So, okay, you need to directly show that G inverse U is equal to F inverse U. Okay. I mean, I believe that this should come from the definition directly. You can try it by yourself. If you are getting difficulty, you can ask, you can email, or you can ask me in the next session. Okay. But this is what you need to show. You understand? Do you understand?
So we're restricting the range of F, is that right?
Range. This is the first part. I mean, yeah, I mean, since we are restricting the, I mean, since we are restricting the range, that's why this equality G inverse U and F inverse U are coming. Okay, because so I mean because if some element which lies outside Fx, so it does not has any effect when you are taking F inverse or G inverse, right? So that's why the restriction. I mean I mean there the inclusion things come some role, but we can't directly use that here. Okay, so in order to prove the G inverse U is equal to F inverse V, we need to directly go with the definition of G inverse U and F inverse V. The the point is, if some element lies outside Fx, so it does not have any effect whether we are taking G inverse U or F inverse V. That's all. Okay. So yeah. So this is and so yeah. So the another part is that if Z is a subset of Y, then the function h from x to z by in the expanding the range. So for a range expansion, what to do? So I mean, so we have map f of x to y, and from y to z, this is the map to the composition container. That's it. Okay. So there is nothing really much to do. And okay, so this is so these are the most important importance of facts and continuity. So okay, so there is one lemma which is named called as testing lemma, and this is actually very useful lemma. In most of the problem, we somehow need to use these lemmas. Okay, so this lemma is known as testing. This goes as follows: let x is equal to a union b, or a be a closed subset of x. Let f a to y and g b to y be continuous. If fx is equal to gx for all x belongs to a intersection b, then the map then the map h from x to y defined by x goes to fx when x belongs to a, and this x goes to, I mean, it is ignored, gx when x belongs to b is continuous. So what is the lemma? So the suppose we have some space capital X and it is union of two closed subsets. Okay, and suppose we have some already maps from the closed set capital A to Y and the closed set capital B to Y. And suppose those two continuous map agrees on the intersection, then those two maps can be clubbed together to get a new map from the whole space to Y by putting those values restricted to each closed sets. Okay, so this is not a pasting lemma. Here only the important thing is that we can club or we can paste two maps only if this condition is satisfied. Okay, so yeah, so yeah, now oh, and also one thing, this lemma is valid only for closed sets. There are some examples where for open set this lemma is not valid. We'll see some examples later or maybe by today also. But pasting lemma is only valid for closed set, not open sets. Okay, and also note that it is valid with finite closed sets. Sorry. So I mean if X is union of finite closed sets, then also the pasting lemma is valid. Okay. So okay. So can anyone please tell how to prove this? I mean this proof is really easy. Anybody please how to prove? So first thing is that so here we have started with some closed sets. Okay. So first, I mean, so in order to check the continuity, it's better to start with some closed subset of Y and then check the thing that the H inverse of that closed set is again closed in domain or not. Okay, so start with some closed set. So now, so let C subset of Y be closed. So now tell me what will be H inverse C? Anybody? Any idea? What will be H inverse C? I mean, look, we have some X and here we have some parts A and B. Okay, and the H is the whole thing. So in this part we have F, and in this part we have G, and in this common portion, this F equal to G. Okay, sorry, in this common portion these things are equal. Now we took some open set U, sorry, with some closed set C subset of Y. Now what will be the H inverse? What it should be?
Um,
Yeah.
F, F inverse
Okay.
intersect G inverse, right?
F inverse, sorry.
F inverse intersect G inverse.
Yes, correct. Yes. Yeah, so this is H inverse C, and of course, I mean, I hope, I mean, okay, so you can say directly, or for those who can't guess it, so
Which
the
is
yeah, so that process that follows H inverse C can also be written as H inverse intersection X because anyway it's a subset of X, so it can so H inverse C is intersection A union B, so which is nothing but H inverse C intersection A union H inverse intersection B. So this H inverse intersection A is nothing but F inverse C union G inverse C. Sorry, yeah, here it should be union. I thought I misheard. Yeah, so it should be 8. Sorry, yeah, here it should be union. Okay, so H inverse C is nothing but F inverse C union G inverse C and F G container. So it is, so this union is a closed set. So that's why H is a continuous. Okay, so this is the testing lemma. So now, one second. Okay, so now there is another thing named as map to the products. So the theorem goes as follows: let f a2x plus y given by f a is equal to f1a f2a for all a belongs to a, where f1 is a map from a to x and f2 is from a to x. Now the theorem is that f is continuous if and only if f1 and f2 are continuous. So now tell me how to do. I mean, and yeah, so this is it. And now note one terminology. These f1 and f2 are known as coordinate functions of f. Okay, so now tell me how to do. So we have some map a to x plus y, and we have an f is equal to f1 comma f2. Now we need to show coordinate wise they are. Okay, so yeah, so one second. What should we theorem like this?
F2 goes from A to Y, not
Yes.
A to X.
One second. Yeah, sorry. Thank you. So any idea how to do? I mean, okay, so it might not be possible to do the both direction. So first tell me, suppose if so, first uh, let's go with the converse direction. That is, if f1 and f2 are continuous, then show that f is continuous. So now tell me how to do. Yeah,
So
yeah, please. Yeah.
say take F1, so F1 inverse is open in what X,
So
right?
yeah, but
F1
yeah.
inverse,
So
and
first,
then the
okay. So
if you inject,
tell me one thing. So you need to choose an open set. So which open set you choose?
yeah, okay, so take an open set in X, U, for example.
No, no. I mean we can't. No. So no. Look, if it's a map from A to X crossword, right? If it's a map from some space to some product, so we need to take open set into the product X crossword, right? Correct. So
Oh, I thought we
take,
were going.
yeah. So take W to be open in X crossword. Okay. So now what to do? So we need to check what? We need to check that if inverse W is open, right? Now how to proceed? So what to do? So what we need to do? So we need to, so let A belongs to F inverse W. We need to show there exist some elements, there exist a basis element of the form U cross V inside F inverse W, where U and V are open in X cross Y respectively. Look, we have X cross Y as a product space, right? So some element. So what is the product topology? Product topology is generated by the elements of the form U cross V, where U is open in X and V is open in Y, and this is the basis of the product topology, right? So suppose A belongs to F inverse W. So what we need to do? We need to produce. So what we need to show? To show A belongs to U. Yeah. To show what? No. Yeah. Okay. To show A belongs to U subset of F inverse W, where U is open in X. If we can show this, then this implies what? This implies F inverse W is open in X, right? So we need to somehow come up with some U which is open in X, right? So how to proceed? So look, the yeah. So we choose A belongs to F inverse W. Okay. So this implies what? This implies if A belongs to W. W is open in X cross Y. So this implies what? If A subset of U cross V subset of W, where U is open in X and V is open in Y, right? So this implies what? This implies A belongs to F inverse U cross V subset of F inverse W, right? Now check that this F inverse U cross V is nothing but F1 inverse U intersection F2 inverse V. So if we can check this, and if this is true, this implies what? If now F1 and F2 are both are open, so F1 inverse U and F2 inverse V, their intersection is also open in capital A, and this lies inside F inverse W. So F inverse W is open. So this is the argument. Do you understand? It is quite tricky, but do you understand? Let me know.
Sir, no, sir.
Yeah, okay. Okay, so let me
I
repeat.
think you mean.
Let me repeat. Sorry.
Don't you mean F inverse of U cross F2 inverse of V? You have intersection. I think you mean cross, right?
You mean this last
Product.
line? You mean this last line, right?
Yeah, you have intersection. I think you mean the product.
No. F is a map from X. Sorry, F is from A to X cross Y, and F1, F2 both are A to X and A to Y. So when we're taking F inverse, so F1 inverse U and F2 inverse U both lies inside capital, right? So the intersection makes sense. Product does not make any sense, right? So yeah. So here the intersection only makes sense. Okay. Anyway, so let me repeat the argument actually. So okay. So we need to check that the map F from A to X cross Y is continuous. Okay. Sorry. So let W be open in X cross Y. Okay. So what we need to show? We need to show F inverse W is open in capital. Okay. So how to do? Let A belongs to F inverse W, and of course A belongs to. So now, so this implies what? If A belongs to W. Now since W is open in the product topology, this implies what? F A lies inside some U cross V which lies inside W, while U is open in X and V is open in Y. Till now, is everything clear? Till now, is everything clear?
Yes, yes.
Yeah. Now,
But,
yeah,
but
please.
W has to be the product of two sets, doesn't it?
Sorry, sir. Repeat.
W has to be the
Yes,
of
correct.
two, product of
Yes.
two subsets. A is a subset of X, and B is a subset of Y, so
Yeah.
W is E cross B.
No, no. The thing is, look. So, what is the basis of the product topology? So, I mean, okay. So, first, tell me the definition of the product topology. So, suppose we have two spaces X and Y. So, how the product topology is defined? Tell me.
It's an ordered, um, it's an ordered pair or
Okay.
ordered pair. X belongs to X and Y belongs to Y.
Okay. So, I mean, what are the open sets in product topology?
U cross V.
No. The thing is, in the product topology, in terms is defined in terms of basis. So suppose, okay, so let me stop this question here. So let me first give the definition of the product topology. Uh, so suppose we have some space X and Y, okay, and in the product topology, X cross Y is nothing but the topology generated by basis U cross V, where U is open in X and V is open in Y. Sorry, what?
Right.
One second.
Right.
One second. This, I mean,
Yeah.
in this, no, in this way, it is in this way, the protocol has been defined. Directly, we can't define these to be all possible opens. We can't declare right like that, because suppose we have some X and Y, okay, and suppose
Yeah.
we define all open set to be of the form U cross V, then suppose this is U and this is V. So basically all open set look like some rectangle, right? But in
Right.
case
Right.
of, yeah, but in case of reanalysis, I mean, of course, I mean, reanalysis metric space, you must have seen that states of this form is also an open set, okay? So that's why we simply can't define
Yeah.
all possible Cartesian product to be the open set, okay?
Right.
So that's why we first
Okay.
declare U cross V to be the basis of the product topology. I mean, first we declare the U cross V to be basis, and we are taking product topology to be the topology generated by this basis. So whenever we are saying that some W is open in X cross Y, and suppose X cross Y is an element inside W, this implies X cross Y belongs to U cross V, which lies inside W, but U is open in X and V is open in Y, okay? So this is the way to deal with the product topology.
Okay.
Yeah. So
Well,
okay.
but
So
just
yeah,
take the restriction. Just
yeah.
take the restriction.
Yeah. So
And
yeah. So here we also got we get if A belongs to U cross W. Now from there what we are getting. So okay. So from now we are getting A belongs to F inverse U cross V subset of F inverse W. Now claim is that F inverse U cross V is nothing but F for inverse U intersection F inverse. Now this is the claim. I mean, if we are done with this claim, then the problem is solved, right? So you need to only prove this claim is true or false. Now I guess this, I hope this, I mean, this claim is very obvious. Just you need to write all possible definition of F inverse U cross F inverse, F1 inverse F2 inverse, okay? Then you will get the intersection actually directly. So that's why I'm writing the proof. So basically what we're getting, A belongs to F1 inverse U intersection F2 inverse V subset of F inverse W. So that's why F is open. Sorry, F is continuous. So now tell me, do you understand, or if you have any doubt, please ask. And if you still, I mean, if you want me to write down the proof of the claim, I'm fine with that. I mean, I can write it down, no problem. So now tell me, do you have any problem in any doubt or any confusion or anything you didn't understand? Please let me know.
So
But
is this true only for sets that for only for topological sets, or is it that this is true for any set?
It is true
Only?
for it is true for any set. I mean, this claim has nothing to do with the topology. It is a simple set. It is simply set theoretical question. It has nothing to do with the topology. Okay, so let me write you the proof also. So okay, so so F inverse U cross V. So it contains those elements A belongs to A such that F of A belongs to U cross V by definition. So all those A belongs to A. Now if A is nothing but F1 A belongs to U and F2 A belongs to V. So it is nothing but A belongs to A such that A belongs to F1 inverse U and A belongs to F2 inverse V, and hence and this is nothing but equal, and this is equal to F1 inverse, sorry, F1 inverse U intersection F2 inverse V. So F inverse U cross V subset of F1 inverse U intersection F2 inverse V. So this is one side, and what about other side? So let no, actually this is the whole argument, because here in each line we have already equal sign, right? Yeah, so this is the argument. So it's a set theory, so we need to start with A and we need to proceed along the definition of F and repeat with C. Okay, so do you understand now? It has nothing to do with topology. Do you understand? Let me know.
Yes, sir.
Yeah,
so
yeah, understand.
um, F inverse of U would say F inverse F1 inverse of U is, say, that's A. F2 inverse of E is B. So F inverse of U would be A cross Y, and
Yes,
F2 inverse of E would be X cross B, and then their intersection would be what you've written.
yeah, I mean,
So it's a product topology. So I'm just having trouble with the intersection, but the intersection of the F inverse has to be a product. So really it's F inverse of U cross Y intersect F2 inverse of V cross X.
yeah, yeah, yeah,
Yep, that intersection.
yeah, correct.
I just had trouble with when you write the intersection because
Mhm.
you went from a product of
Yeah,
two sets,
because
just
the
a
map
single.
is from A to X cross Y. So inverse are coming inside the left portion. Left side has only one domain, capital A. Left side is not a product. So anyway, it has to be intersection. There is no option for product, right? It's my guess that like since domain is a single, domain is not a product, so it can never be product, right? So in that way. in that way. Yeah. Anyway, so okay, so this is one part, that is which part? Yeah, so this is the one part, that if both, if the coordinate functions are continuous, then the given map is also continuous. Now we need to do the reverse, that is, if the given map is continuous, then the coordinate functions are continuous. Okay, so for that, okay, so for that first, okay, so observe one thing is that, so what are the coordinate functions? So we can write f1 to be f composed by 1, or we can write f2 to be f composed by 2, where phi 1 in the first coordinate projection, and phi 2 is the second coordinate projection. Okay, so now if we need to show that it's continuous, we need to check that both f and phi 1 continuous, then we can apply the position law. So we need to, so actually we need to show now that phi 1, phi 2, these maps, projection maps, are continuous. If we can show this, then we are done, right? I mean, do you understand why we need to show that the projection maps are continuous maps?
Yes, sure, of course, yes.
Yeah. So
So,
now, yeah, so pi 1 is from x cross y to x. So now, so start with an open set. I mean, okay, so first try by yourself that why the projection
so,
map.
take U as an open set
Yeah, okay.
in X, right?
Yes.
So pi 1 inverse of U is open in X, and then cross that with Y, it's open. Y is open.
Correct. So this is anyway open in x cross y in the product topology. So pi 1 is continuous. Correct. Very nice. And due to similar reason, pi 2 is continuous.
Yeah.
So this f1. So this f1 and f2 are both continuous maps. Okay. So moral of the story is the following. Suppose we have some maps from the space to some product in the um, if the coordinate function is continuous, then the whole map is continuous. Okay, this is the moral of the story. And of course, you need to remember one thing, that projection maps are continuous maps. Okay, now once, yeah, once. Hmm. Okay, now there is another theorem. I mean, sorry, it's not a theorem. It's a exercise actually. Yeah. Suppose f a2 b and g c2d are continuous maps. So now we are defining f cross g from a cross c to b cross g, from a cross c to f a cross g. Now show that f cross g is continuous. So how to do? I mean, so we have some map in here from product to product. So you need to start with an open set in b cross g. You have to show that their inverse image of that set under f cross g is open. So first try it, then I'll write the solution.
So what does that small a cross c stand for? Is it normal multiplication?
No, no, no. I mean, no, no, I mean, it's not. It's just, it is a Cartesian product. I mean, okay, sorry. Instead of a comma c, I wrote a cross c. So let me write it down again. Yeah, a comma c. Sorry for that. A comma gc. So now try to show that f cross is continuous. So yeah, so the process will be same as the last exercise where we saw a map from a to x cross y. In that exercise, whatever the way we have used this, the same way we need to use it. First, we need to start with the open set of b cross d, and we need to choose an element in f cross g whole inverse of that open set. Now, then we need to go along with the definition with the product topology, and somehow we need to come up with the open set so inside f cross g whole inverse w. So just try it yourself. Then I will.
You know that F and G are continuous, right?
Yeah, yeah, of course. I mean, yeah, if and j continuous.
You take an open subset in B and an open subset in D.
No, no, I mean, we can't take any open sets in B cross T, right? I mean, we need to choose an open set in B cross T, right? So any open set
Yeah.
of B cross D, if we take any open set, look, any open, so U cross V, where U is open in B and V is open in D, this U cross V, this type of elements are the basis elements. So not all open sets of B cross D are of the form U cross V. So what you need to do, you first need to choose an open set and you then need to choose a point inside that open set. Then you will get some elements of the form U cross V inside that open set. Okay, you directly can't start with some U cross V. Understand?
Okay.
Yeah, yeah. Let's try.
So you can't take an open set in B and an open set in D. That's what you're saying.
Yeah, directly we can't. I mean, we need to start with any open set, right? But any open set is not necessarily the form U cross V, right? So that's why we can't directly start with U cross V. We need to choose an open set, and if we take any point from the open set, then we'll get any element of the form U cross V which lies inside W. I mean, inside the chosen open set, containing that point in that way only.
So, so you take W
Yes.
in B cross D, and just take some open set W in B cross D, right?
Yes. Okay.
Um, and F inverse of W, F inverse of W.
I mean, what is? I mean, we need to consider F cross J whole inverse W, right? Just F inverse W doesn't make any sense, right?
No.
So yeah. So we need to show that F cross G whole inverse W is open, right? So we need to show this is open. Wow, it is open and A cross. Correct. So what we will do? We will take a
Yeah,
point.
yeah,
Yeah.
you have W there, right? You have W. Where's W?
Yes, W. Yeah, F cross whole inverse W. We will
Yeah.
show this thing as
So,
open in A cross C, right?
so
Yeah.
what you have there, F cross G inverse W.
Yeah.
So you take that back to intersect that with A, right?
I mean, how? I mean, F cross the whole inverse W is a subset of A cross. It is not a subset of A, not a subset of C. It has some part of A, some part of C. So we directly can't take any notation. I mean, you need to go with the usual way. So we need to show that if F cross G whole inverse W is open in A cross C. So what we will take, we will take a point A comma C, which lies inside F cross G whole inverse W. And now we will try to show that A cross C belongs to U cross V, where U is open in A and V is open in C, and that U cross V lies inside F cross G whole inverse W. This is what we need to show. Okay. So this implies what? This implies FA comma GC belongs to W. Now we know that W is open in B cross G, right? So this implies what? FA comma GC belongs to U cross V, which is subset of W. This U is open in B and this V is open in D. Okay. So this means what? FA belongs to U and GC belongs to V. So I mean, okay, so this is what we got. Now obviously F cross G whole inverse U cross C is equal to F inverse U cross G inverse V, and this two lines gives what? A comma C belongs to F inverse U cross G inverse V. So this one is what? A comma C belongs to F cross G whole inverse U cross V, subset of F inverse W, and this thing is yeah, this F inverse F cross G whole inverse U cross V is equal to this thing, and F and G are individually continuous, so F inverse U cross G inverse V is open in A cross C. This is open in A cross C, and hence it is a subset of F inverse W. So this is the, I mean, yeah. So this is the argument. So yeah. So I mean, so finally, what we have done, we have, so we took a point A comma C belongs to F inverse W, and we are able to show that A cross B belongs to some open set of A cross some open set of C, which lies inside F inverse W. So this is what we wanted, and this is the thing. So I mean, this sorry, this is the output. So is it clear to everyone, or it got missed?
Yeah, that's good. Yes,
Yeah,
understand.
fine. Okay, so once, yeah.
Are
So
you going to post? You're going to
yeah.
post these slides? The
Sorry,
slide?
which points?
Are you going to post the slides on this session on the website?
Yes, NPTEL team has uploaded the link to the course portal.
Yeah. Okay.
So you can check that in the portal there is one tab named as live sessions or something like in live discussion, live sessions, something like that. There is a tab. So inside the tab, the links are there.
Okay.
Fine. So okay, now there is one exercise. Let A be a source of X and let F A to Y be continuous. Okay, and let Y be house dog. Then show that if F may be extended to continuous map G from A to Y, then G is uniquely determined. So this is a question. So what does it mean? So we have some continuous map from A to Y, and A is a source of X. Now suppose, and given that Y, that is codominant is Hallström. Okay. Now suppose F can be extended to its up to its closure. So now we need to show that if the codomain is Hausdorff, then the extension map is unique. So this is what we need to show. So do you understand what we need to show? Yeah.
Yeah, I
Okay.
understand.
Yeah.
Yeah.
Yeah. So the first of all,
I'm not.
yeah. Sorry.
I'm
Please
not
go
sure
ahead.
how to prove it, but I understand.
I mean, no problem. I mean, look. What you need to prove actually. Suppose there are two extensions. You want from A closer to Y and G to A closer to Y, two extensions of F. Then we need to show G1 is equal to G2. So yeah. So of course it's not true. So tell me how. So yeah, I mean it's quite tricky problem. So that's why let me give the hint actually. So look, Y is a Hausdorff space. So in the last live session, we have seen one fact that Y is space is a Hausdorff if and only if its diagonal is closed in Y. And also this is one fact you may need to use, and second fact, I mean this fact we need to use, and we have proved this fact in the last session. The second fact is that suppose f x to y is a map, then if continuous, if and only f of a closure subset of f of a whole closure for any a subset of what subset of x. So you need to use these two things in order to prove that exercise. Now try to use this and try to solve. You can take it. You can take your time, no problem. For Hausdorffness, we need to use the diagonal as a closed set, and for the and there is another fact you need to use, that a map is continuous if and only if of a closure subset of a whole closure for any subset. You need to use these two facts together in order to show that G1 is equal to 2. So first, try to recognize or try to understand that why. I mean, how we can use the closeness, or how in this question this diagonal map will, sorry, this diagonal set will come into play. Diagonal of y contains those elements of y cross y such that both coordinates are equal. Now, in our question, how you can come up with diagonal of y cross y? Think about it first, then try to solve. Okay. You can take your time. I should back up some minutes.
Okay.
Anybody understand it? Anybody has done it? Anybody?
So if
Yeah.
you take A cross A and Y cross Y,
Sorry.
oh, this I got in trouble this last one. Never mind.
Okay, that's
I have to work on this, yeah.
so. What about others? Anybody?
Well, what if you take G1 inverse of some set cross
Yeah. So yeah. Okay. So let me read
cross
it.
two inverse?
So take the function h from a closure cross a closure. Okay, sorry. So choose the function h from a closure to y plus y. Okay. How is defined? Defined to be a goes to g1a, comma g2a. Okay. Right. So if we're defining such a function, then what we need to show? We need to show that h of a closure lies inside delta, right? If we can show, I mean this the diagonal. If we can show, then we are done, right? Correct. If we can show this, then we are done, right?
Okay.
Yeah. Now observe that since G1 and G2 are both extensions, so a h of a is equal to G1a, G2a is equal to fa, fa, which lies belongs to delta whenever a belongs to cap a, right? So this means what? H of a is a subset of delta. Okay. Now, we took G1, G2 to be the extension, and I mean the continuous extensions G1, G2 we took. And so since G1, G2 continuous, so this H is also continuous. Okay. Now since H is continuous, so this implies what? H of a whole closure subset of delta closure. Okay. Now since H is continuous, so H of a closure, which is subset of H of a whole closure, and this H of a whole closure is a subset of delta closure, and our delta closure is equal to delta because y is house drop, so delta is a closed set. So we get what? We get H of a closure subset of delta. So I mean this is what we are trying to show, right? And this we got. So I mean this is the argument. Do you understand? Or it's just a bit confused? Or should I repeat the argument?
Yeah.
No.
What's the statement about Hausdorff again? It says the diagonal is continuous.
Uh, yeah. So look. So h of a is subset of delta. Okay. So from here we are doing that. We took the closure h of a closure subset of delta closure. Now y is Hausdorff, so its diagonal set is closed set. So delta closure is equal to delta. And now since h is continuous, so h of a closure is a subset of h of a whole closure. So I mean, so here I mean in this line actually we have used this delta closure is equal to delta. That is a diagonal is a closed set, and also we use the fact that h is continuous. And together this things we get h of a closure subset of delta. So this is the argument. Is it clear to everyone? Is it clear to everyone?
Yeah, so the delta is closed,
Yeah.
right?
Yeah, correct.
Because the other one's house door.
Yeah. And the other part continues. That's why the subset closed. So yeah, so this is how it. So one second. Hmm.
So could you repeat this?
Yeah, yeah, sure, sure. So okay, so let me write it down. So suppose let G1 and G2 are two continuous extension of F. So we start with some two continuous extension G1, G2 of small f. Okay. So we need to show that G1 is equal to G2, right? So this thing, I mean, this G1 is equal to G2. This thing can be written as follows. We define a small h from a closer to y cross y. A goes to G1, G2, right? So G1 is equal to G2. This is same as saying that image of H subset of diagonal of Y, right? Till now, is everything clear?
Yes, sir.
Yeah. Now, since G1 and G2 are extensions of what of F, so G of H of X is equal to G1 of X comma G2 of X is equal to Fx comma Fx, and each, yeah, I mean, it is an element of boundary where X belongs to capital. Okay. So the H of A is a subset of delta. Till now, is it clear?
Yes, sir.
Yeah. Now, since G1 and G2 are continuous, so H is also continuous. Okay. So H of A closure, subset of H of a whole closure, and this is subset of delta closure, and delta closure is equal to delta because delta is closed set as Y is house door. Okay. So what we got? We got H of A closure is a subset. Sorry, H of A closure is a subset of delta, and this is what we initially tried need to. I mean, this is what we need to show that and domain of domain of H is A closure, right? So this is it. So H of A closure subset delta, that is image of a subset delta. So I mean, this is the argument. So now, do you understand, or if you have any doubt or confusion?
Yes, sir. Thank you, sir.
Okay. So once. Okay, so there is another important fact you need to remember. The thing is, so what is the definition of continuity? The definition of continuity is that the inverse image of open set or the closed set is open or closed respectively, right? So instead of taking random, I mean, instead of taking arbitrary open set, we can work with only basis elements. So that is to say, if you can show that open set, I mean, inverse image of any base element is open, or the inverse image of, sorry, I mean, this is open set, yeah. So, so this is another exercise that suppose f of x to y, then if is continuous, if and only if inverse b is open in x for all basis b of y. So if you can check that inverse image of base element is open in x, then f is continuous. So this is the exercise. Please try to solve it. I mean, of course, it's easy, but just let me know the solution.
This is just the definition, right?
Yeah, correct. So I mean, one side is of course definition. What about the converse? It's, I mean, this is a if and all statement. So what about the converse? So I mean, so for the converse, so we need to assume that it is known that all of the inverse image of all these elements open. So now we need to start with some arbitrary open set u of y. So how you can come up with, I mean, how we can connect all basis elements with this with the u. I mean, how we can connect basis elements with some given open set. Tell me.
Well, you just use the basis, you just use the axioms of a topology, union of
Yes.
open set.
So yeah, correct. So suppose u is open in y, so this will be what? U can be written as union of basis elements, arbitrary union. So now if inverse u is nothing but arbitrary union of inverse base elements. Now if it is known that if inverse b alpha is open for all u, so this, I mean, so then if inverse u is open, I mean, yeah, so this is the argument. So in some problems we might directly need to use only the fact that inverse image of base element is only open. So this directly implies that if it's continuous, we don't need to check all possible open set because it is not always practically feasible. Okay. So yeah, so for the time now. So yeah, it is almost 9 now. So okay,
So
so
we
that's
need
it.
to prove that.
Yeah,
We
sorry,
need to prove that. That's already proved.
sorry, I couldn't get it.
Do we need to prove that, or we
Yeah, I
already
mean,
proved that?
yes, yeah, I mean, I have already proved that.
Yeah, yeah.
Do that proof. Yeah, so this is it. Okay, so I mean, okay, so let's just end here. We meet in the next live session, but please do one thing. In the chat, I gave a Google Meet link, sorry, Google Form link. uh, Please mark your attendance by submitting the Google Form. I'm sending that again in the chat. Please give your attendance. It is important.
Okay. Can I ask a question?
Yeah, sure.
It seems like in the introduction we're spending a lot of time on metric spaces.
Uh,
In
so
the course, we're spending in the first 4 weeks we're spending a lot of time on metric spaces.
yeah,
But this is a course in topology, right?
yes, yes. Like
So is that just to get intuition or?
no, it is like it is some kind of brush up thing because many things of the metric, many properties of metrics is directly transferred to topology. So if metric space, I mean, so metric space is like a preliminary thing, but it's a topology course. Yeah, I mean, we will see some exercises involve metric space, but preliminary this course is targeted to topology, not the metric space or not the nominal spaces. But for the sake of understanding, God's sake of simplicity, he started the metric space, no nominal space. Then we'll start the topology. Actually, okay, I mean that's when the all its equivalent, no problem. Okay,
Just a
so
review, a review and a motivation for topology.
uh,
Just a review,
yeah, so look,
and so motivation to see where
yeah. So the thing
topology.
is that, there is some motivation. So I mean, so uh, suppose suppose you have some circle and you have a sphere. Okay, suppose you have circle and a sphere. Now, of course, circle and sphere are not same thing. Means there does not exist any homeomorphism from circle to sphere. It is quite obvious. At least you can visualize, right? But the thing is how to prove this. In order to prove this, we need to use some concepts or some theorem for topology, namely fundamental group, which is a part of the topology itself. So
Right.
these are some invariants under homeomorphism. So using these techniques, we can say that between some elements, between some spaces, there exists a homeomorphism or not. That's why first we need to read the topology. Then there is a one part of the topology, namely algebraic topology, which deals with these things only. Okay. So this is the motivation what till now what I understood from topology. So this points at topology works as a preliminary things, but but the problem like between two spaces, they will there exist in homeomorphism or not comes in separate topic, namely the algebraic topology. And in order to understand the higher things, we need to understand the basic things. That's why we need to read the points topology. That is the only motivation.
Yeah.
Okay, fine. Yeah. Okay.
Yeah. I mean, yeah, I get that. I mean, you have to understand
Yeah.
in order to do algebraic topology, you need to understand the underlying point set
Yeah.
topology.
Yeah. Correct.
Yeah, right. And usually they don't talk about that in algebraic topology. They just talk about groups and stuff, and they never talk about the underlying
Yeah, because
topology.
because both are separate thing, right? So I mean, if somebody talks about this thing like topology, then the whole course will go into topology, not the topology itself, right? So that's right.
Yeah, well, I mean, you get into
So yeah, so that's why this course is named the points of that's
CW
why
complexes
PS1.
and the
Yeah,
compact
yeah,
open topology
yeah. This thing will
and
come gradually in this
factor
course.
generated and that kind of thing.
Yeah, this thing will come across. Don't worry.
But we're not there yet.
Sorry.
We're not there yet, so we have a ways to go.
Yeah. I mean, this. Yeah, it will come in this course itself.
Okay.
Possibly within 1 month, most probably.
Okay.
Yeah. Okay. So bye. So I'm leaving the call.
Okay. Bye.